Assalamualaikum and good day everyone. We are Gutri from section 6. Today we are going to present our project entitled Design of a Centrifugal Pump for Water Transfer System. Before we start, let me introduce our group members. I am Nuzatu Putri binti Yusani, together with Dayana Atika Sazwani binti Abang Imad, Muhammad Yusuf bin Kamarul Azman, Muhammad Syami Azri bin Shadri, and Rismaya Silabah Ramli. For today's presentation, I will be presenting introduction and related theory. So let's begin with the introduction. Water is very important for irrigation, especially to maintain healthy grass at the UTHM football field. Instead of relying only on treated water. This project proposes using water from Tasik G3 and pumping it to an elevated storage tank. This approach is more sustainable and help reduce the use of treated water. The main objective of this project is to design an efficient piping system that can transfer water from the lake to the storage tank. Besides that, we also need to select suitable components such as the centrifugal pump, HDPE pipe, valve, fittings, and storage tank to ensure the system operates efficiently. To evaluate the system performance, several fluids mechanic calculations are carried out, including flow velocity, Reynolds number, head loss, total pump head, pump power, and pipe thickness. These calculations help ensure that the system is safe, efficient, and cost effective. That's all for the introduction. Now, I will explain which is related theory. This project is based on several fundamental concepts in fluid mechanics. First is the fluid mechanics principle, which use the continuity equation and Bernoulli equation. The continuity equation is based on the conservation of mass, while Bernoulli equation is based on the conservation of energy. These equations are used to determine the required pump head and analyze the fluid flow in the system. Next is the Reynolds number. It is used to determine whether the flow inside the pipe is laminar, torsional, or turbulent. This is important because the flow condition affect the friction loss in the pipeline. The next theory is friction factor and head loss. There are two types of head loss. Major head loss, which occurs due friction along the pipe, and minor head loss, which is caused by valve, elbows, and other fittings. Both loss influence the pump performance and energy consumption. Another important theory is pipe thickness, which ensures that the pipe can safely withstand the internal operating pressure. Finally, we use a centrifugal pump, which converts mechanical energy into hydraulic energy. It is widely used because it provides continuous water flow, has high efficiency, and requires relatively low maintenance. That's all from me. Thank you.
Okay, so as you can see for the design specification, we have choose seven specification to make sure our pipes is doing good. So for the first is the fluid inlet blade angle, which is we choose 25 degree for a smooth water entry and reduce losses. After that, we choose outlet blade angle with 30-degree angle, which high hydraulic efficiency. Then we choose inlet blade with our inlet blade width is 40 millimeter, which ensures smooth inlet flow. And our outlet blade width is 25 millimeter. It is to reduce discharge losses. After that, our inlet radius is 60 millimeter, which is to make the water smooth entry the piping. And outlet radius is 180 millimeter. It is to generate the required heat for our pipes. And lastly is the impeller speed. Our impeller speed is 2900 rpm, which is this is the standard speed with good efficiency. So that's all for me. Thank you.
Next, I'm gonna present about design analysis. First, we calculate the velocity using the continuity equation. The velocity is 11.67 meters per second. Next, the Reynolds number was calculated as 2.92 million, indicating turbulent flow, which is suitable for this pumping system. 4.2 Head loss analysis. The major head loss due to pipe friction is 16.64 meter. After adding the static head of 15 meters, the pump must generate a total head of 31.64 meters. The pump must overcome both elevation and friction losses. 4.3 Pump power. The hydraulic power required is 177.7 kilowatts. Considering an efficiency of 80%, the input power increases to 222.1 kilowatts. Therefore, a standard 225 kilowatts motor is selected. And the last part is 4.4 Impeller analysis and summary. Finally, the impeller has a peripheral velocity of 54.66 meters per second. The backward curved blade design provides efficient energy transfer and stable operation. Overall, the design meets all project requirements and is suitable for transporting water to the touch and football field irrigation system.
Assalamualaikum and greetings to Dr. Akmal. My name is Muhammad Syamil Azri bin Shadiri. My matrix number is CD2400365. Now, I would like to present the result and performance evaluation of our proposed centrifugal pump design. This table summarizes the final result obtained from the design calculation presented in the previous section. The pump successfully achieved the required flow rate of 0.573 cubic meter per second with a flow velocity of 11.67 meter per second. The calculated Reynolds number is 2.92 times 10 to the power of 6, which indicates that the flow inside the pipe is fully turbulent. The major head loss is 16.64 meters, resulting in a total pump head requirement of 31.64 meters. In terms of power, the hydraulic power required is 177.7 kilowatts, while the required pump input power is 222.1 kilowatts, assuming a pump efficiency of 80%. Overall, this result confirm that the proposed pump design satisfies the required operating condition and design specification. Next, I will discuss the performance of the proposed pump based on the calculated result. First, the pump successfully delivers the required flow rate of 0.573 cubic meters per second, which meets the design requirements stated in the case study. The calculate total pump head is 31.64 meters. This is sufficient to overcome both the static head of 15 meters and the friction losses of 16.64 meters along the pipeline. The Reynolds number is 2.92 times 10 to the power of 6, confirming that the flow is fully turbulent. Although turbulent flow increases friction loss, the selected pump is capable of supplying sufficient energy to maintain the required flow rate. Based on the power analysis, the required pump input power is 222.1 kilowatts. Therefore, a 225 kilowatt motor is selected to provide a suitable safety margin and ensure reliable operation. As shown in the chart, approximately 47.4% of the total pump head is used to overcome the evaluation difference, while 52.6% is used to overcome friction losses within the piping system. Finally, I will discuss the efficiency and feasibility of the proposed pump design. In this project, the pump efficiency is assumed to be 80%, which is a typical value for medium-sized centrifugal pumps used in industrial application. Based on the final design result, the proposed pump successfully meets the required flow rate, generates sufficient pump head, and operate within all specified design constraints. This indicates that the design is technically feasible and suitable for transporting water from the river to the storage tank. However, Several simplifying assumptions were made during the preliminary design stage. Minor head loss, mechanical loss, and pipe roughness were neglected to simplify the analysis. For the future improvement, the design can be enhanced by including all minor loss, performing a cavization analysis, and validating the result using manufacturer pump performance curve. In conclusion, the proposed centrifugal pump provides a practical, reliable, and efficient solution for the required water transfer system. Thank you.
Assalamualaikum, my name is Dan Latika Suzani Mita Iman, Mathematic Terminal CD240127. I'm going to present about our conclusion. So, in conclusion, this project successfully designed and analyzed a centrifugal pump system to transport water from Tasset G3 to an elevated storage tank while meeting all the specific design requirements. Using the continuity equation, Bernoulli equation, and Reynolds number, and Grassi Wishbach equation, the system achieved the required flow rate of 0.573 cubic meter per cube, with a total pump head of 31.64 meter. The calculated Reynolds number of 2.92 times 10 to the power of 6 indicated fluid turbulent flow, while the required hydraulic power of 177.7 kilowatt and input power of 221 kilowatt justified the selection of 225 kilowatt motor for safe and reliable operation. The chosen backward curve impeller operating at 2,900 RPM provide efficiency, energy transfer, and stable performance, making the proposed system suitable for the UTHM football field irrigation system. Although the design was based on several simplifying assumptions, it provides a strong foundation for practical implementation. Future work should include detailed loss analysis, pump performance verification, cavitation assessment, and optimizing using commercial pump data to further improve system efficiency and reliability. Okay, that's all from me. Thank you.